All right, let's give this one a try with an example here. And in example one, we've got this spinning device. And can you see how this track here, as that spins, is going to both compel the ball to move this way, but it's also going to force it to go outward on that track. So they gave us a theta in terms of t equation, and they gave us an r in terms of t equation, which is interesting. So we can find then the magnitude of velocity and acceleration at a time t equals 1.5. So we're going to use the polar coordinate system. This is a good opportunity for that because of the way that it has like a fixed axis with something that is forcing it to spin around, right? And it's not going to be a constant radius. Obviously, they gave us that r function. And so this is a good opportunity to use the r theta coordinate system, polar coordinates or cylindrical coordinates. So bam, there it is all at once. But really, we've just got a lot of derivatives we've got to do, right? We have the r equation they gave us to start. Take a derivative. There it is. There's r dot. Take a derivative again, r double dot. There it is, right? And since we're doing it in terms of time, we don't have any chain rules or anything weird going on there, right? We're just bringing down the 3 here, making that t cubed to t squared, doing it again to get to there, right? Same thing for the theta equation. Do a time derivative once, do a time derivative twice, and we've got those. And so if we plug in 1.5 seconds, these are all the values that we get for those, right? From there, we had our equations for the components of velocity and the components of acceleration, right? We had the r dot was the r component of velocity. So that would just be 0.65675 here. And then r times theta dot, right? So plug in r, there it is. Plug in theta dot, there it is. That is our theta component of velocity. So our total velocity is just the magnitude of those Pythagorean together. And so we've got 2.57 meters per second total. So a lot of kind of plug and chug once we've got those figured out here, what our R's and our thetas are for all three of those. We just got to remember that, theta dot isn't the acceleration in the theta, or R double dot isn't the acceleration in the R direction. We have to calculate it using these different things, right? R dot, for example, and theta dot, those are not simply the components of velocity. We had to plug them into those derived formulas for the R and the theta component of velocity. So as long as we do that, it's kind of a lot of plug and chug. We'll do the same thing one more time for acceleration, right? We had this equation for the R component, this equation for the theta component. And so you'll notice the R component isn't simply just R double dot. The theta component isn't simply just theta double dot. It's a lot more than that. And so we come up with that by plugging in all of our values here, right, that we solved for earlier, plug those all in for our R's and thetas and simplify. We will get 10.75 for the theta piece, negative 17.33 for the R piece. Does that make sense to have any negatives in this one? Let's think about that. Could we have a negative in the R direction? Not for this example, right? Well, no, we could. We could have it could be slowing down how much it's moving outward. Be hard to have a negative velocity, I guess. But it could be slowing down how fast it's going out. In this case, we found out in the R direction. Nope, it is, yeah, it is slowing down somehow. And then in the theta direction, it's speeding up, right? It has a positive acceleration. So all together, we've got 20.4 meters per second squared as our magnitude for that one. So not too complicated as long as we can figure out what these are, right? If we can solve for the time derivatives of r and theta, from there it's mostly just plug and chug into those equations for velocity and for acceleration, and then making sure that our answers seem logical for the situation.